So what do waves have to do with simple harmonic motion? Well, basically, think of what a wave is it's a displacement of something from equilibrium, right? A water wave, we displace the water from its equilibrium position, and that creates something that propagates outward from that displacement. So, while simple harmonic motion is a displacement from equilibrium sort of in place that oscillates up and down, a wave is a displacement from equilibrium both in place that oscillates up and down. Think of a water wave as something, if you look at one point in the water, just at one point, the water molecules are essentially just going up and down. They actually are going a little bit in circles, but they're going up and down. So they're oscillating like as in simple harmonic motion, but that is also propagating out in all directions from that. So a wave is just simple harmonic motion that then propagates out from where that motion originates. So, you think of, for example, a string wave, a wave on a string, a guitar string or something like that. You look at any point on that string, a point on that string just oscillates up and down from equilibrium in simple harmonic motion. Now, you look at the shape, it's not exactly parabolic, but remember, we showed that what shape? Sorry, the shape of the potential energy curve of the displacement of the mass of the string from equilibrium, etc. may not be exactly parabolic, but they approximate to be parabolic. So it's approximately simple harmonic motion. That's important to understand because then our ideal waves are approximately going to be modeled by sines and cosines, just like simple harmonic motion is modeled by sines and cosines. And yes, this was just supposed to be my hand waving at you when we're talking about waves. Okay, so waves are really just simple harmonic motion if you look at a point in space, but it's also motion that then propagates through space. So let's take a wave that we can approximate as simple harmonic motion. I'm going to call it a simple wave. That's not often the terminology you see, but a simple, a straightforward wave, a single frequency wave, a simple wave, something that propagates. That can be approximated by simple harmonic motion. And let's take the string that's shown in the upper right-hand corner here, and let's just look at a point on the string, and just ask, how does that point move with time? With time, we know it goes up and down and up and down and up and down with simple harmonic motion. So in time, if we call this the x direction is the direction of wave propagation, right? The wave propagates to the right and to the left. The direction of wave propagation is the x direction. Then the displacement from equilibrium, or the amplitude, is in the y direction. The amplitude would be maximum displacement from equilibrium. We're going to be careful about that terminology. And so what we find for a simple wave is that in the y direction, in the y direction, that y equals y max, right, the amplitude, times the sine of omega t plus phi. So there you go. That is any point on that wave oscillates up and down with the equation of simple harmonic motion. Cool. So this wave, if we graph it as y as a function of t, it'll just go on forever, as long as that continuous wave goes on forever, as long as there's no friction. The wave is going to go on forever with time, and we can do various things like say, the period is the distance, the time between when it repeats itself, so that's the period. We know the amplitude, y max, or amplitude, that's a, y max equals, that's y. Y max equals a. What else? Remember, phi just has to do with initial conditions, right? In this case, phi is actually, for the wave that I just plotted, phi is equal to 0. Y max is initial conditions, it's how hard we pluck the string. And omega is 2 pi over t, 2 pi over the period, which we don't need to write in terms of any physical properties of the string. It has to do with the period of oscillation or the frequency of oscillation, right? It's 2 pi f, and it has to do with the note that we're playing, right? The frequency of the wave. I'm going to do something which might probably is not confusing, but don't lose me here. So what I did here in the bottom is I was talking about a point on the wave and how it oscillates up and down in time. But what about the wave in space? In space, I already had a picture of the wave, how it looks in space right here. And in space, it also looks like a sine wave, right? So if I take, so in the bottom was a snapshot of a position in space as time progresses. But what if I freeze time and I just look at the equation of the wave as far as space goes? Then we're going to have y, right? This the purple curve in the upper right hand corner is y equals y max. It still is it is displaced from equilibrium by some maximum distance, and it's a sine wave, but it's not a time-dependent sine wave. It's, hold on a second, try that again, a bit better picture. So now I'm looking at an equation, a spatial equation rather than a time-based equation. And in space, right, we want it to be a function of distance, x, and then it's going to be some, we're going to call it kx. Careful, because k is not spring constant. And I'm going to show you that k is different than omega. So down here, it was y equals y max sine omega t plus phi. That's the time dependence. The spatial dependence is going to look the same. It's going to have the same function, y equals y max sine kx plus phi. K is not spring constant. K is actually called wave number. K is wave number. That's the name of the constant. It has nothing to do with spring constant. It just happens to have the same letter. And it's not omega, right? You can see that because what k is if the wave repeats itself, if it in distance this much, right? This is lambda. This is the wavelength, right? Wavelength is the distance over which it repeats itself. Then, by the same argument that that omega is 2 pi over period, then k in this case, k is 2 pi over lambda, because the sign has to repeat itself every 2 pi. So y equals y max sine 2 pi x over lambda plus phi. Because the sign has to repeat itself every 2 pi, and the wave repeats itself every lambda, then every time, if whatever phi is a constant, let's say phi equals 0. If x is lambda, then sine of 2 pi is 0. If x is 2 lambda, then we're back to sine of 4 pi, which is 0. If x is 3 lambda, sine of 6 pi is 0. So we get 0. The function repeats itself every time x increases by a factor of lambda. Hence, k, the wave number, is defined as 2 pi over lambda. So we now have a spatial dependence for a wave on a string or any general wave, and a time dependence for any general wave. Okay, so now let's let time flow. If time flows, we know that this wave peak is going to move to the right. This wave peak is going to move to the right. The entire wave moves to the right. And yeah, it bounces off the wall and moves to the left. Let's just talk about moving in one dimension for now, or in one direction for now. The wave peak, that's the wave speed, at speed v. Now think about, a point on the wave is going to move up and down as the wave is moving by it. And so how far does the wave have to move in order for the point on the wave to move up and down one full cycle? The wave has to move a distance lambda, and it takes a time t to move the distance lambda, right? So if the wave peak goes, if one wave peak goes from, let me find a different color. If this wave peak goes from here to here, in that time, the point is, any point on the wave will move all the way down and all the way back up again. So each one has gone through a full cycle. So it takes a time, capital T period, for a point to move on the wave, lambda. That is the speed of the wave. The speed of the wave is lambda over t. I shouldn't put that in a box yet. The wave speed is lambda over t, And that is also lambda times frequency, which you already knew, right? Because t is 1 over frequency. V equals lambda over t, or lambda times f. You can go ahead and combine the spatial dependence with the time dependence to get the equation of a single frequency wave. This is called single frequency waves because they're talking about a single, a single omega that represents the wave, a single frequency. These aren't complicated waves. They're single frequency waves, a single omega, a single wavelength, a single frequency. So we can combine the time dependence with the spatial dependence to see how a single wave function describes a moving wave. Since phi, the phase, is defined just as from initial conditions, let's just forget about that for now and let's just set it equal to 0. Say that's what our initial condition is going to be in order to derive the equation of a moving wave. We can add back in phi later and just say we can make it arbitrary. And let's just say that we've got a wave that has a spatial dependence of a sine kx0 at some t, at some time t. T0. Some later time, right? Because the wave moves at some later time t, because the wave moves at speed v, then x is equal to x0 plus v times t. Some later time t, a wave that's moving at a constant speed v, which it is moving at constant speed, has an x at a later time, x as a function of t, or x as a function of t is equal to x0 plus vt. Oh, my iPad is messing me up. And so that means that x0 is equal to x as a function of t minus vt. And that means we can plug that back into the equation of a wave, the spatial dependence, and get x equals a sine x as a function of t, I'm sorry, k, whoops, that's k, k, x as a function of t, and we don't have to write it as a function of t, we know if we don't put a subscript on it that it means it progresses with time, x minus vt, and that we can distribute the k, a sine kx minus kvt, and remember that v is equal to f lambda, and so therefore kv is equal to f lambda times k, which is 2 pi over lambda, and the lambdas cancel, so that's 2 pi f, which is, ta-da, omega. So what we get is y equals a sine kx minus omega t. Kx minus omega t. And the a is just y max, right? Okay, so that is the equation that includes both the spatial dependence and the time dependence of the wave. And we can go ahead and throw phi back in there and say we can change the initial conditions. Right now we have at t equals 0 and x equals 0, then y equals 0, right? This one is at t equals 0 and x equals 0, there y equals 0. But if we don't want the initial conditions to be defined as that, we can just throw in a phase factor and say, in general, y equals a, or y max, times the sine of kx minus omega t plus phi. This is the general equation, or simplified equation, because we're assuming simple harmonic motion of a single frequency wave, right, where omega equals 2 pi f and k equals 2 pi over lambda. This is the equation that we were graphing on that wave simulator that I showed you on the computer. Let me just make sure you understand. If we say, let's just make t fixed, and we look at what is the spatial dependence of this wave, right? The spatial dependence of this wave looks like that, y as a function of x for fixed t, and where we would find that this is the wavelength, etc. for a fixed time. Sorry about the mess. And this time dependence is, let's take a snapshot. I'm sorry, let's look at one point on the wave and just ask what the time dependence is, right? It's also a sine wave. And again, it doesn't necessarily start at 0. That's defined by phi, where this distance here is period. So this equation is the same wave that we've been talking about all along. And this is a wave that if we then start time going, right, then if we start time going, then this top one is going to start moving in the plus x direction. Each peak, and I always, each peak moves, I mean, not each peak, but the entire wave keeps moving in that direction at constant speed, and v is equal to f lambda, which is also, you would find, omega over k. That's f lambda. Omega over k. You can figure that out for yourself.